So last time we were talking about chiral shift reagents, and although I didn't display it in the packet, is actually the very first paper I published back when I was an undergrad that used chiral shift reagents. I want to talk now about a more common, at least contemporarily, way of determining an enantiomeric purity, and that is chiral derivatizing agents. And as I said before, and as we've mentioned in the course, an R compound and an S compound enantiomers have the exact same spectra. You can't tell an R enantiomer from an S enantiomer by NMR, and you can't tell that from a racemate by NMR. NMR is a chiral, and it takes some type of diastereomeric interaction, whether external like a chiral shift reagent or internal like a diastereomer, to get distinction of signals. So one way to go ahead and achieve this so that you can see a distinction between your two enantiomers is to take a reagent that reacts with the enantiomers to make diastereomers. That is, to take a chiral reagent and derivatize your molecule. So I'll show you two popular ones. So one of these is called MTPA, or more commonly referred to as Mosher's acid, or Mosher's esters, or what you make. So this is MTPA, methoxy alpha trifluoromethyl phenylacetic acid, but as I said, commonly referred to as Mosher's acid. And the idea is that you've got a carboxylic acid, so it can react with an amine or an alcohol in the presence of a coupling agent, or you can make the acid chloride. So I'll say couple with alcohol or amine to make an ester or an amide. And at that point, it's great because now you get diastereomers, but what's even nicer is that you get two handles that are sharp singlets. A methoxy group, so you'll get a tight line in the NMR spectrum, and also a trifluoromethyl group, which gives you a tight line in the F19 NMR spectrum. So you get two handles, whereby now you can see distinct resonances for the enantiomer of your molecule. So that's one. Another useful reagent or set of reagents are isocyanates, and particularly the isocyanate of phenethylamine is nice. So this is R alpha methylbenzyl isocyanate. And isocyanates react with amines to give ureas. And I'll show you an example of this, although not exactly with this reagent, in just a moment. But these would be two good examples. One of the nice things with Mosher esters, so often you go ahead and you form, your alcohol may in fact be the source of the stereocenter. So you may have like R and R prime and have a stereocenter on your alcohol. And maybe I'll draw this with a little squiggly line to indicate that we don't know the stereochemistry. one of the nice things of Mosher esters is there are empirical rules for telling the absolute stereochemistry. So you can often not only tell the enantiomeric purity, but tell if you have R or S, and that's very handy to do. Anyway, I want to give you an idea, an example of a problem. And again, this is in the handouts, but not particularly necessary. I think it's in handout 3, a paper I published. And I'll just tell you about a little bit of a real research problem that I was working on, that my group was working on, where we had occasion to basically use a chiral derivatizing agent. So we had developed a synthetic method to make isocyanates of amino acids. And so we started with S amino acids as the hydrochloride salts. And in typical examples, we would have a methyl ester group. And we would treat the amino acid with phosgene, and we did this with some pyridine. And this gives rise to the isocyanate. So phosgene is the double acid chloride of carbonic acid. The pyridine basically allows the amine to react with the acid chloride and then causes elimination to give rise to the isocyanate. And the worry that we had was whether this stereocenter was intact. In other words, did the chemical reaction, did the reaction of the amino acid hydrochloride in generating the isocyanate, did it possibly epimerize this stereocenter? The alpha proton of an ester is slightly acidic. We didn't know about the effect of this group, and we also didn't know about the effect of the pyridine base. So the question here was, did we also have the enantiomer? And if so, how much? And so I'll write sort of a big question mark over that. So as I said, we couldn't tell enantiomers apart by NMR spectroscopy, but we could tell diastereomers apart. So in order to analyze what was happening, we took our phenethylamine, so basically the amine or the enantiomer of the amine isocyanate I just showed. So many amines are available in enantiopure form, so you can buy this amine 100% enantiomerically pure. And amines react with isocyanates to give rise to ureas. So I'll draw the product of the first reactant there. Oops, this is my bad here. This is supposed to be a phenyl group. All right, so on the one hand, we might have a molecule where we have an R stereocenter and an S stereocenter. On the other hand, if we have our impurity, if we have our epimer, then we would also expect to see, so I'll put this in parenthesis, we would also expect to see the diastereomer, which would have 2R stereosectors. So we took an NMR spectrum, and what we observe is one set of peaks. So that suggests that we had only this diastereomer, but of course it's possible for the diastereomers to be coincident. So we wanted an authentic sample of the other diastereomer. But in order to make the other diastereomer, we would have had to start with the enantiomer of the amino acid. So there's a very nice trick that we use. We go ahead and we simply, in a separate reaction, instead of using whoops, and I meant to over here, let's see, we actually, my bad, that's supposed to be the going back here, getting ahead of myself. So we started with the R over here. So we went ahead and we started with the S compound. And so we started with the S-phenethylamine, and we prepared an authentic sample of the SS diastereomer. And the SS diastereomer has peaks that are distinct. And for example, the two methoxy groups, depending on which amino acid we use, these two appear well separated. They're separated by about 0.02 to about 0.03 parts per million. In the NMR. And that's nice because a sharp singlet separated by a couple of hundredths of a ppm basically is completely non-overlapping. And we saw none of this peak in this sample. And then the final experiment we did to establish that we were indeed enantiomerically pure in our isocyanate was to go ahead and spike in about 1%. I think we actually spiked in 0.05% or 0.5% into the sample of this to demonstrate that even at a level of 0.5%, even at 1% impurity, we could, 1% enantiomeric impurity, we could pick it up. So that told us that we were greater than 99% EE. So that's a nice example, or at least from my perspective, is a nice example of use of a chiral derivatizing agent to establish the enantiomeric purity of your compound. And you could do the same thing in your own research in a synthetic methods project.
James?
Yeah.
Could you please explain the spiking and how you knew that it was over 99% again, please?
Okay, so what we saw in the NMR spectrum of, so let me erase the top line. All right, so what we see in the NMR spectrum is basically a big methoxy group and nothing else, right? You know, this would be about 3.4, 3.3 ppm. So that's what we see over here. And I put a little tick mark just to indicate what we're seeing. When we spike in the little bit of the diastereomer, we see a little peak here. From this diastereomer. So that's the idea. It's almost like an HPLC trace, where this is the methoxy of the RR compound, of the RS compound, and this is the methoxy of the RS compound, and this is the methoxy of the SS compound. Does that make sense?
Yes, thank you.
You're welcome. And remember, normally a peak is about maybe 1 hertz, slightly more than a hertz, maybe 1.2 hertz wide. So if you've got a separation of a couple of hundredths of a ppm, at 500 megahertz, that separation is about 10 hertz. So those lines are very well defined. The distance between the lines is way bigger than the fatness of the peak, so you can completely resolve them, and that's nice. Other questions or thoughts on this? All right, I think at this point, I want to talk about another technique that I find very useful. And in fact, right now, a graduate student in my group, Zing, is probably going to need to use this technique in order to establish that one of his compounds is pure for the purposes of publication. And for your peers who have just gone through their second year reports, many of them were very concerned about getting samples, getting spectra of their compounds pure when they did a synthetic project or a project aimed at making a reagent. And so if you have extra peaks in your NMR spectrum, you can worry, oh my goodness, are these extra peaks part of my molecule? Or are they a chemical impurity? And I think that sort of will tie into two things that I'm talking about next. So first thing I want to talk about is XZ, exchange spectroscopy. And it's useful for identifying conformers or other species in moderately slow exchange. And in terms of the operational aspects, it's the same pulse sequence as nosy or rosy. And the exchange cross peaks appear on the same side as the diagonal. And all of this will make more sense when I give you a concrete example. And from an operational point of view, there's one thing that's key here. So you basically need to adjust your temperature so that the peaks broaden slightly. And by slightly, I mean by a couple of hertz. Because what that broadening is indicative of is that chemical exchange is occurring on the order of hundreds of milliseconds or 100 milliseconds, and that's going to give rise to a cross peak. So let me explain what I mean here. And I think the first thing to do is to start with one of the handouts. And I think this is in handout 1, and it's not quite at the end, but it's pretty close to the end. So I'm going to share my screen. All right. So remember, handout 1 was from this book, 200 and More NMR Experiments. And I ended up going into my office. Remember, I was talking about this last time, this book by Berger and Braun. And I was saying what a nice book it was because it gives examples of lots of experiments. And then I mentioned this other book, which they published subsequently. Actually, one of them did, along with Phenethylamine, 50 and More Essential NMR Experiments, which talks a little bit more about running the experiments, and both give operational examples of this. Anyway, so the pulse sequence, as I said, is similar to a nosy or a rosy pulse sequence. There's a key element of mixing time. And the example that they give here is dimethylformamide. Now, DMF we talked about before. Can you see my screen okay?
Yes.
All right. So DMF we talked about before has 2 methyl groups in there. And those methyl groups give rise to 2 sets of resonances, one at one position, one at another position. When we talked about NMR spectroscopy, I think you had a problem both that showed exchange at various field strengths for the instrument, and we also talked about variable temperature NMR. We said that the barrier to rotation about the amide is about 18 kilocalories per mole. And so in this example, they would have warmed up their DMF solution to a point where the peaks, the singlets, were just getting a little bit fatter, and they run an XE spectrum. And so this is your diagonal. And normally you would just see, I have a methyl group here and a methyl group here. You'd wonder if they are the same molecule. We saw these examples also in the homework problem that had the propionamide of benzyl ethylamine, where we had two sets of peaks. And the question was, why is this molecule giving two sets of peaks and why are they of unequal intensity? This is the same problem that you'd have in your own research or coming to a second year report or a paper somebody might encounter when they're trying to establish, is my compound pure? Well, if you can show that those two peaks are associated with the same molecule, you can show that they're not chemical impurities and also get a better understanding of the dynamics of the molecule. So in the Xe spectrum of this warmed sample of DMF, what you see is a cross peak between the two methyl groups. And what that means is the methyl group that is, it would be this one, the methyl group that is cis to the carbonyl group, and the methyl group that is trans to the carbonyl group, they're swapping places. So on the time scale of the experiment, on the time scale of hundreds of milliseconds, the methyl group that's cis to the carbonyl group, we get rotation about the bond, about the carbon-nitrogen bond, the carbonyl-nitrogen bond. And the methyl group that is cis to the carbonyl group trades places with the methyl group that is trans to the carbonyl group. Does that make sense? All right, I want to give you a real example from my lab that I thought was really, really cool. And I think this is handout number 4, and I accidentally closed that one. Okay, so this is a handout number 4, and it was a paper that a graduate student in my group, Sang-Woo Kang, was doing. He had made this molecule over here, and the molecule consisted of 4 unnatural amino acid residues, all the same residue in this particular case, hooked into a great big macrocycle. And so you'd expect all 4 of them to be the same, but that wasn't what he was seeing. What he eventually figured out, he saw 2 sets of resonances. One set of resonances from a symmetrical conformer, a square conformer, and one set from a rectangular conformer. And he wanted to establish that these sets of resonances actually belonged to the same molecule and figure out what was going on. So he did an Xe experiment, and here's a slide from the work. So basically, we saw 2 sets of resonances, and I'm just going to focus in on one region of the spectrum. I think that's enough for us to look at here. So let's just pay attention to this region right over here, where he sees a set of resonances associated with a CH2 group that's next to this oxygen here. And we've got a bunch of resonances there. There's also one other resonance in there. And so, oops, where's his expansion here? It's down here. That's what I was going to do. So down on the bottom here, we're going to focus in on this resonance here. And so we're focusing in on this region over here. I think that's probably the easiest to do in this complicated spectrum. And what he sees is the resonance that he attributes to the square conformer, which he calls A. So this is our diagonal again. Gives cross peaks with two of the resonances from the rectangular conformer. Now, the rectangular conformer has basically two cis amides in it. And so you have OR groups that come from the residue that's on the, from the amino acid that's on the transamide, and OR groups that come from that on the cisamide. So there's two types of OR groups, whereas in the square conformer, in conformer A, there's only one type. So he sees that the resonance of the CH2 group crosses with both of the rectangular resonances. So basically, if we look down here, the resonance of the square conformer gives cross peaks with both of the rectangular resonances, because there are two of them. And what's interesting, so you also see, but more weakly, exchange of the rectangular ones, so the two different sites with each other, but they have to go through the square. So basically it takes longer. So you go one rectangle to square to the other rectangle. So we see a weaker cross peak between those. So from my point of view, this was a pretty cool set of experiments, because it established that this very messy spectrum, all of the peaks could be accounted for, and it helped us understand what all of the peaks were associated with, and that they all belong to the same molecule. So thoughts on XE? So I mentioned that Xing is now looking at this experiment. So he's developing an amino acid building block, and it's protected with a Bach group. And we think that some extra peaks in the proton NMR may be associated with rotamers about the Bach group. And so one way to establish that those extra peaks are from the rotamers is to show that they're in chemical exchange with the other rotamer. And so that's what he's going to be using this for. All right, I want to talk about yet another technique that I found to be useful. And that technique is called DOSY, or diffusion ordered spectroscopy. And what DOSY is useful, it's a 2D technique, or sort of a pseudo 2D technique. It separates spectra by diffusion coefficient. And since the diffusion coefficient, the motion of the molecules, depends roughly on their molecular weight, it effectively gives you separate spectra for the higher molecular weight and lower molecular weight compounds. So it's useful for mixtures and identifying impurities. So for example, let's suppose that you have some extra peaks in your NMR spectrum and you're trying to understand what's causing them, and you think that they are from, say, a reagent or a byproduct of the reagent, and they're not your main molecule. And the reagent has a very different molecular weight, or you think that they're from a solvent, but you're not sure. This can be a very useful technique for identifying these types of extra peaks. And so I think for this one, I'm going to go back to handout 1. And it's the very last part of the first handout. So I'm going to share my screen with you. All right, so again, this is from the 200 and more NMR Experiments book. This talks a little bit about the technique, and as all of these nice little chapters do in the book, it gives some literature references, which is a good place to get started in reading about it. And here's the example on the very last page of handout 1. And what they did in this example was they made a mixture of different compounds. So this was a demonstration where they took triethylene glycol, they took N-butanol, they took methanol, and they took water, and they mixed them all together in an NMR sample. And this is what you see in the spectrum. So here's our H1 NMR spectrum. And it's kind of complicated. Obviously, they knew what all of these different peaks were because they knew what they mixed together. You often won't have such a luxury when you're looking at what might be an impurity in your compound and you're wondering, hey, what's causing these extra peaks in my NMR spectrum? And so they went ahead, they mixed them all together, and then they ran a DSy experiment on them. And in the DSy experiment, you have things separated by diffusion coefficient. I just want to get my notes over here. So basically on this axis, you have your diffusion coefficient. And so with a very high diffusion coefficient, you see a cross peak here in this area. And that tells us that this peak over here is the water peak, right? We trace this up over to here. At a slightly lower diffusion coefficient up here, we see another peak. That peak corresponds to the methanol. Methanol is still a very small molecule. Then yet at a lower diffusion coefficient, we see 4 peaks over here. These correspond to the butanol, the CH3. I'll just write this as butanol. There's the CH3 group. Here are some of the CH2 groups. And here's the last CH2 group. And then at still the lower diffusion coefficient, we see 2 more peaks here. And those peaks correspond to the triethylene glycol. So my laboratory uses this technique because when we're looking at our molecules, we'll have equilibria between monomer and dimer or tetramer. And so we're interested in identifying, what are the relative molecular weights of the species, or what is the oligomerization state? Is it a dimer? Is it a tetramer? And so we can calibrate and say, okay, a monomer has this diffusion coefficient. A dimer will have a diffusion coefficient that's about 0.8, as big as that of a monomer. A tetramer will have a diffusion coefficient that's about 64% or 63% that of the monomer. So we can basically measure the molecular weight of our species from the DSy spectrum. Thoughts or questions? All right, I think the last technique I want to talk about here is water suppression. So a lot of molecules that my lab is interested in are water soluble. And a lot of these molecules are peptides and proteins, so they have NH groups in them. And we want to be able to see these NH groups in water. Now, the problem is that the NH groups, if you dissolve up your sample in water, you'd normally, in order not to get a big water peak, you dissolve it in D2O. But the NH groups exchange with the D2O so that you won't see them. In other words, the NH groups become ND groups on the time scale of your handling the sample. So you need to run your sample in water in order to be able to see the NH groups. But water is 55 molar H2O. And you're not going to be able, so that means you have 100 molar or 110 molar of protons. They are going to dwarf, they're going to saturate your spectrum compared to your millimolar concentration of compounds. So you've got to make the water peak disappear. So there's a couple of ways of doing this. So basically what you do is you use gradients or other pulses to go ahead and eliminate the H2O peak. And this allows you to observe your compound, observe your NHs. I'll say observe some NHs. And by some NHs, I mean amide NHs, yes, amine NHs, often no. And typically what you do is you need a little bit of deuterium in there for a lock signal. So typically what you do is use water with D2O, just a little bit of D2O in a 90-10 mixture. So most of your protons still stay as protons on the nitrogen and you get very little deuterium. And I want to show you a couple of handouts on this just so you can see what the technique entails. And I think probably the most useful handout for starters is going to be a couple of pages back in number 1 here, in handout number 1, where they talk about one of the water suppression techniques in the pulse sequence. This means gradients, where you're messing up your Z magnetic homogeneity, the magnetic homogeneity along the sample. So you're sort of unshimming the sample with pulses from the magnet. And the example they give over here in this handout is a sugar molecule. Sugars typically don't dissolve in organic solvents, so sugars only dissolve in water. But the problem with using water for your sugar is that then you're not going to be able to see your OH groups. I guess you still can't see your OH groups over here. So honestly, I'm not sure why they're doing it. I think it's simply what they had in this particular example. But basically, this would be the water peak, and it's been made to disappear by the pulse sequence.
James, are you meaning to share your screen right now?
Oh, yes, thank you. Okay. So backing up. So this is in your handout. And this is what I was talking about with the gradients being applied in the pulse sequence. And then this was an example of a sugar molecule dissolved, I think it's lactose they're using here, dissolved in water. And the water peak, which normally would be gigantic, has been made to disappear. So this is done in 9010 H2O, D2O. And so the water peak has been made to disappear by the gradients. Now, this particular example isn't super useful because they're not seeing the OH groups, but you could go ahead and apply the same methodology to a peptide or protein. And I think my last handout here is probably, well, I guess, oh, did I not pass that along? Okay, I guess I didn't pass it along, but very briefly, what I will tell you is that typically in a peptide or protein, as long as your pH is somewhere slightly either neutral or better still slightly acidic, you can see the NH groups. And I think that's where I will end today's lecture and maybe take a few final questions.